All right. So now questions about the H&R diagram. O, B, fine girl, and kiss me stuff. So we have the O stars, which are not just the largest, they're also the most massive. And they're not just the most massive, they're also the most luminous. And they're not just the most luminous, they're also the hottest on the surface. So the hottest, the most luminous, the most massive. They also die more quicker than all the other stars. So this guy here, the most massive ones maybe last for 1 million years, 2 million years, 5 million years. So they die very quickly. B stars, on the other hand, might take them 100 million years to die. A stars will last at least, some of them last 500 million years, a half a billion years. F stars, they last for billions of years. Mostly less than 3, 4 billion years. G stars, they can last a long time, 6, 7, 8, 9, 10 billion years is how long the sun is going to last. When I say how long it's going to last, I'm referring to how long they stay on the main sequence as a main sequence, G star, F star, what have you. K stars and M stars, they pretty much last forever. M stars last for like 1 trillion years. K stars for like 400 billion years. So these guys don't have to spend much energy. These are the Priuses of the starry world. Little tiny cars, little tiny engines. These guys are like Suburban, Chevy Suburban. You just have to get gas every couple of miles, This is the O star. Also, most of the stars in the sky are M and K stars. This is something you better take a note of because it's going to be on the exam. What kind of stars are in our neighborhood? The neighborhood of the sun is full of M and K stars. In fact, 95% of all the stars in the sky are K and M stars. They're everywhere. When we look around us within 10 light years, they're all M and K stars. They're all little tiny red dwarf stars, little tiny dwarf K stars. There's only one A star in the neighborhood. And because nobody else is there, the A star happens to be the star of the neighborhood. It's the brightest star in the sky. We call it Sirius. Sirius is the brightest star in the entire sky. And it's not that fantastically luminous either. But because it's close, it's only 8.6 light years, it appears to be the brightest thing in the sky. So when we look in the sky, which one of these stars do we see? Well, it turns out that we see not that many O stars. Not that they're not luminous, they're very luminous. There's just not that many of them in the sky. You really have to look to find an O star. B stars and A stars, there's a lot of them. In fact, because they're so luminous, that's what you're looking at. When you look at the sky, you don't see stars that are close to us. You see stars that are very luminous. And that's something we figured out about 100 years ago. So you can write that down. When you look in the sky, we see stars that are very luminous, not the stars that are very close. They didn't know that till about 100 years ago. They thought maybe because they're close, but that's because they're just luminous. I think I'm done with this guy, so let's get to the next. Black holes. All right, so a black hole has a singularity where the star used to be like an O star. When supernova, the core of the O star collapsed, the rest of the O star came down, and then it expanded afterwards. It ricocheted off the core and went supernova type 2. What's left of the core, if it has more than 3 times the mass of the sun, it's going to become a singularity. In other words, the core of a red supergiant star that has more than 3 times the mass of the sun is going to collapse, 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 and collapse until it disappears from this universe completely. It's gone. There's nothing there. Where there used to be a gigantic sun like an O or B or A star, now there's nothing. It broke the fabric of space and time and just left the universe. Now, what we have instead is singularity, a point mass that has the same mass as the old core of the star. All we know about this singularity is that it has mass, rotation, and charge, nothing else. Surrounding it, there is something called an event horizon, where space is falling into the singularity faster than the speed of light. So nothing can escape from inside of an event horizon, assuming that you don't have a spacecraft that can go much, much faster than the speed of light. But of course, in movies like Star Trek and Star Wars, all those spaceships travel faster than light. So is it possible they can go in and out of an event horizon? It's possible. All right, and this explains how big this event horizon is. The more mass you have, the more gravity you have. The more gravity you have, the bigger the size of your event horizon. So if the Earth was going to turn into an event horizon and a black hole, if you get the whole Earth, you shove it down into a singularity, it would have an event horizon approximately the size of a ping pong ball. That'd be the size of the event horizon. Singularity doesn't have any size. All right. So there's going to be quite a few of these questions on the exam. Question is going to be like, what is the classification for this star? What is the classification for this star? Something like that, right? They're not going to be exactly in the same spot, but they're going to be the same kind of thing. So let's classify these. Luminosity class belongs to a group of stars. The group that we call the main sequence here, their luminosity class is 5. Roman numeral 5. So these two stars are main sequence. So the first thing you do when you get a question like that, you go down, down, down. This one is a B 8.5. And because it's in the main sequence, it's a Roman numeral 5 for luminosity. So this is a B 8.55. This one here, you go down. F1, that's for the temperature and spectral class. And so this guy here is F15. What if there was one here? You go down, this would be K35, like that. That's how you classify them. So make sure you know the luminosity classes. Red giants have a luminosity class of 3. So this one here, again, you go down. This is a G7-3. And I'm not going to give you any trick questions. I never do. So there's no questions like, is this a G6-3 or G8-3? Nothing like that. So G7 is going to be, exactly it. So this is a G7-3. 3 for giant, 5 for main sequence. Supergiants, 1. Luminosity class 1. Now, if you watch the video, you'll see that I made a change here. I put in M03 because for some reason I put down M01. So that's an error. M0 is over here, and that's not an M0, right? M0 would be like over here someplace. So if you watch the video, make sure you look to see what I'm saying is different from what is over here. I say M01, but it says, there's a little thing here that says M31. I think it says no, M31. Okay? All right, so that's the questions on the H&R diagram. All right, so again, let me ask you guys a question. Where on the H&R diagram are the hottest stars?
G7.
I'm sorry?
G7 over there, and red giants. No supergiants.
Where on the main sequence are the hottest stars? See, it says surface temperature here, right? Surface temperature.
Would it be like O? Like O1
Well, it's O0, but
or O0.
what I want you to say is upper left-hand side. See, on the upper left-hand side of the H&R diagram are the hottest stars. This is where the temperature is, right? This is M stars, coolest. O stars, hottest. So here is the hottest stars in the sky. So where are the coolest stars in the sky? Over here. Lower right-hand side. Where's the most luminous stars in the sky? Up here.
Top right.
Up here. Upper right would be the most luminous. I want to ask you for the most luminous, but I'll ask you maybe where's the coolest stars? Where's the coolest, where's the hottest, stuff like that. All right. Okay, let's get to the rest of the questions. So I'm going to go over your questions, see if I can give you guys some hint as to what kind of questions will be on the exam. So when I look at the sun, I see the photosphere. Photo means light. Sphere means light. So sphere of light, that's what I see. So what am I looking at, right? I'm looking at those bubbles, right? Those bubbles are continuously coming up, exploding on the surface of the sun. What are those bubbles called? Granulars.
Cells.
Convection cells, that's right. Those convection cells are called granulus. The effect of all these granulation, that's what we call granulation. Whole bunch of granulas. Remember, granulation is like sugar is granulated, salt is granulated. A lot of things are granulated. You can see it on the package. On sugar, it says granulated sugar, right? So that's what granulation is. All right, what about sunspots? Why are sunspots dark?
Because the sun's brighter than the
Because they're
sunspots.
cooler.
Okay, very good. So who said that?
Trevor
I
Shaw.
heard it. I'm sorry, who?
Trevor Shaw.
Trevor. Thank you, Trevor. Shaw, S-H-A-W, right?
Yep.
Thank you, Trevor. That's right. So the sunspots are very luminous, but they appear to be dark because the sun is hotter and more luminous. So who said hotter? It was a lady that said hotter.
I said because they're cooler.
The sunspots are cooler than the sun.
Cooler.
That's right.
Correct.
Very good. So I'm sorry, what is your last name?
Costa, C-O-S-T-A.
Oh, you're making a killing today,
Yay.
Cindy. Cindy the killer. All right. So now, what happened to these sunspots between 1645 and 1715?
There were very few of them. Very
That's
little.
correct.
Almost
Do you
none.
recall what they're called? Cindy.
Minimum sunspot. It wasn't sunspot minimum, but
No, it's called Maunder period or Maunder minimum.
under minimum.
Maunder, that's right, Maunder. So there was no sunspot, so we had a little tiny mini ice age, basically. All right, so does anybody know what the solar corona temperatures stay at millions of degrees? Why doesn't it cool down to space?
Because it's drawn to space because it's cool. Space is cool.
Right, space is cold, exactly. So why doesn't it cool down? It should lose heat.
Because of dark matter.
No, it's not because of dark matter.
Is it because none of the electrons are bonded to
That's right.
the nuclei?
Because all the atoms are ionized, so they don't have electrons to cool down. Very good. Who's this?
Trevor Shaw.
Ah, Trevor is making killing too. All right. It's a good thing to be ready today, man. I can tell you that much. Good answer.
Professor,
good answer.
what was the reasoning for that again?
Trevor, can you repeat yourself, please?
It's because none of the electrons are bonded to a nucleus, so they won't go down in level.
So if you don't have any electron, what do? If you don't have an electron, you can't cool down, right? Because normally the electrons go down, you emit energy. If you don't have electrons, then you're out of luck. Okay, so the chemical composition of the sun is also important. So take a look at the chemical composition of the sun too. It's in one of those videos. What is the chemical composition of the sun? What is the sun made of, you know?
Helium and hydrogen?
Well, there's other stuff too, right? So take a look. There's a chemical composition I left there for you. All right, let's see. So there'd be a question on prominences. There's questions on filaments. There's questions on sunspot cycles. So prominences, filaments, and sunspot cycles. If I said the sun is older than all O stars, would I be correct?
No.
No.
Of course I'll be correct. Why would I be correct? How old is the sun?
5 billion years old?
Pretty close, close enough to get a point. That's Cindy, right?
Yes.
All right, I'm getting to know you now. That's right, it's 4.6 billion years old. So you should know that. You should know that the sun is 4.6 billion years. Your son is going to ask you, your daughter is going to ask you when they go to, you know, like 5th grade or something. So you better be ready for this kind of questions, you guys. Don't Google it when they ask you. You'll be embarrassing yourself when they ask you, how old is the earth, mommy, daddy? Mommy, daddy, how old is the earth? And you're going to say, I don't know. Can't do that. So how long does it take an O star to evolve, Cindy? Approximately, we're not asking you.
In about like 5 million years.
Okay, 10 million years. So the sun is 4.6 billion years. Why would not the sun is older than all the O stars?
F star's 4 billion years, G star's 10 billion years.
Right. So why wouldn't the sun be older than all of the O and B and A stars?
Because it's a result of a supernova, and that's why it's trace element. That's where the trace elements come from.
Okay, you're not listening to me then. You're not hearing me exactly. So please listen one more time. Why wouldn't the sun be older than all of the, main sequence O, B, and A stars? Since the O, B, and A stars don't live any more than, let's say, 100 million years, sun is 4.6 billion years, it should be older than all the A and O and B stars, right?
Yeah.
So even if the supernova remnant is exploded, supernova remnant is not an O star, it's a supernova remnant. Do you see?
Is it because it's not repetitive like a nova? Am I?
I am not getting you.
Because you
I'm
said
sorry.
novas can be repetitive, supernovas only happen once.
Okay, what does nova has to do with this question that I'm asking you? I said the sun is older than all of O, B, and A stars. Correct or not correct? That's all I said. We didn't talk about novas. We didn't talk about supernovas. We're talking about O, B, and A stars. O, B, and A stars are only called O, B, and A stars because they're on the main sequence. Once they evolve, they become red giants, red supergiants, and stuff like that. I just said sun is older than all O, B, and A stars. Okay? I think Cindy got it. Noah, did you have a question?
No, I thought that O, B, and A stars don't last as long as the smaller stars generally. So that's why the sun would be older.
Exactly. The sun is older than all those stars, right? Those stars are all young, right? In fact, next week I'm going to tell you they're called population 1, the youngins. Like you guys are all youngins, right? Look at you guys. You guys are babies, right? So I'll be like a red giant and you guys are like, O stars. You guys are ready to go running. All right. Just trying to help you guys. Make sure you guys know the H&R diagram, like, oh, be a fine girl and kiss me, like that. Make sure you know that. Okay, of course, you're going to watch the videos before you take the exam, so I'm not too worried. All right, okay. There's going to be 3 questions on the hydrogen fusion, right? So what happens when 2 hydrogen atoms collide at the core of the sun? Well, 2 protons collide. I have a video just for that. It's only 2 minutes long. So you get 3 points for watching a 2-minute video. So please get the details though. You need to know the details of fusion. Why doesn't atoms in your room fuse? Does anybody know? How come in your room there's no energy production from fusion? The atoms in your room are colliding all the time. There's lots of atoms in your room. You don't see them, but because you don't see, they're invisible. But my room is filled with atoms. How do I know? Because I'm breathing it, right?
It's not hot or dense enough.
Right, it's not hot or dense enough. Very good, man. Cindy is getting an A in today's class, I think. I think you're getting your A today, man. Did you study already, or is this something you remember, Cindy?
I'm just going off of, I had to rewatch some of the videos from a couple of the lectures.
Oh man, I like you, Cindy. I'm beginning to have you as my favorite student now.
I'll stop. Thank you.
Yes. All right, so evolution of the old stars, right? Evolution of old stars is going to have a few questions, like, write down please, like supernova type 2. What the heck is it, right? What stops the neutron stars from collapsing? How big are the neutron stars? I'm going to try to make a video for you guys tomorrow morning, but just in case, make sure you can watch the old video that we talked about evolution of massive stars. I believe it was, when was the last time? Time before that, we talked about evolution of massive stars. Please. The stars that are supergiants, they have core collapse. When they get to iron, then the core collapses because iron, you can't fuse iron. That's it, you're done. And then you go supernova and you become a crab nebula and all that. Okay, question. Is it true or is it false? If, let's say, the sun collapses 1,000,000 times, would it become 1,000,000 times denser?
True.
True, that's right. It is correct. Like, remember, we're talking about neutron stars. We said a teaspoon of a neutron star is 1,000,000,000 tons. You guys have any idea what 1,000,000,000 tons is? It's like a billion.
It's like a mountain.
Huh?
It's like a mountain.
Billion mountains? No, it's not 1,000,000,000 mountains.
No,
It's 1,000,000,000 Priuses. 1,000,000,000 Priuses. That's a teaspoon is 1,000,000,000 Priuses. All right, Justin, thanks for putting your camera on, man. This is the second time I've ever seen you, dude. Sheesh. All right. So the evolution of both sun-type stars and massive stars, key. It's going to be quite a few questions. Right. How do stars transport energy from the core outward? There's a video just on transportation of energy
convection.
inside of stars. Convection is correct. Which stars have a convective core? Which stars have the radiative core?
M and K, I think. M and K, the red ones at least.
No, all the massive stars have convective cores.
The OBA.
The OBAs, yeah, they have a convective core. So they bring fresh fuel into the core. They need to bring fresh fuel. It's like one of those jet planes that travels super fast. You have to refuel it. Like if you go to war, you have to keep refueling it like 3 or 4 times. You can't just fly it forever. After 2 hours, it needs to get refueled. So it continues to have refuel. So they have to get refueled. So they bring in fresh fuel. They bring in fresh fuel, fresh virgin. Virgin means untouched. They bring untouched hydrogen into the core to burn it. They got to, man. Those O stars have like 10 times the mass of the sun, like millions times the mass of the earth worth of gravity. They have to protect themselves or they'll die. All right. What part of black hole has the mass of the black hole?
The singularity.
Excellent. Who said that?
Trevor Shaw.
Oh, I can't believe that. You guys can be the only one answering these questions and getting points. Sheesh, thank you, Trevor. You're my second most favorite student now after Cindy.
Yeah.
Thank you. I'll remember that when I'm grading. Go, Trevor, he deserves an A. Even if you get a C, still, he deserves an A. It should be in my head. Okay.
Thank you.
You're welcome. All right, let's see what we got here. What is the H&R diagram? The H&R diagram is a diagram of
Luminosity.
versus
Temperature.
temperature. Okay. Who's this? I hope it's not Shaw again.
It's Noah.
Ah,
Noah
Noah. Tenny, right?
Yes.
Excellent, Noah.
Is it, you said between temperature and what?
Luminosity.
Thank you.
It's a graph of temperature versus luminosity, surface temperature, right? Okay. There'll be a question on novas, there'll be a question on supernovas. So at what point do you make all the elements heavier than iron in the universe?
Supernova.
Which kind of supernova? Supernova type.
What's that, Professor?
Supernova type what? There's different supernovas.
So type 1A.
No, type 1A just makes helium. When it explodes, you just see a whole bunch of helium coming out. No, it's the other guy. Supernova type 2, the core collapse. That's where you make all the matter. Okay, let's see. Okay, almost done, you guys. What time is it? Oh, we got plenty of time. So far, I've seen 3 questions on fusion. What the heck are planetary nebula? Noah, can you tell me, why are some stars red, some stars blue?
Isn't a correlation between temperature and luminosity?
Surface temperature, no, it's just temperature. Surface temperature determines your color. If you're 6,000 degrees, you'd be yellow. If you're 20,000 degrees, you'd be blue. If you're 3,000 degrees, you'd be red. It's just surface temperature. Oh man, that red lobster and crab got me, man. Crab nebula got me. I'm going to Red Lobster right now after class. What stops the collapse of a white dwarf? What stops the collapse of a neutron star? What's a Pauli exclusion principle? Does anybody know? Pauli exclusion principle. No two particles can occupy the same place at the same time. So I got 2 protons here. They can't be in the same place. How are they going to be in the same place? You can't, right? So no 2 atoms, no 2 particles can be in the same place at the same time. That's it. You can't be there. Impossible. It's called a Pauli exclusion principle. That's just how the universe works. That's what stops the collapse of neutron star. Okay, that's called neutron pressure.
You said that stops the collapse of a neutron star, and
Yeah.
it's called neutron pressure. Stop.
Well, it's got neutron pressure, not because it, but yeah. So what stops the collapse of a white dwarf, Cindy?
Geez.
You haven't read that part yet, huh?
Oh, I've been reading it. I'm getting all confused with things now. But
It's
okay.
white. It's electron pressure, right? You'll get there. Don't worry.
The part of it that keeps confusing me is the electron bits. That's the one that I keep getting stumped on. So I have
Electron. Did you say electron bits?
the electron bit of what we're studying. So that's where I get confused when it's.
Oh, you know what electrons are, right?
Mhm.
Oh yeah, electrons are little tiny things. They don't act the same way as protons. They're weird. It's like protons. You put them together in a small confined space, temperature goes up. You put a whole bunch of electrons in a tiny space, temperature doesn't go up. They're just weird. Electrons are just supernatural, right? Well, protons are supernatural too. The whole universe is supernatural. You guys are supernatural. Everything is supernatural. Jeez.
So the white dwarf is stopped from collapse by electrons. And
Yeah.
how do the electrons stop that collapse? Just to be clear.
Electrons refuse to be compressed. So you really want to know, I'll tell you. You know how, like, if you have an electron around the proton, like, let's say this is an electron, all right? There's a proton. You know how, like, you have orbits, right? In the first orbit, you can have 2 electrons, right? In the second orbit, you can have 8 electrons, like that. So if you have more than 2 electrons, what happens?
They jump.
They go to the next level, right? They get this magical energy and they go to the next level. So you can't put any more than 2 electrons in that first orbit. If you put 2 electrons in the first orbit, there's no room for anything else. That's it. 2 electrons is all you can have in the first orbit. And so you go to the next orbit. Well, that's the same thing with the electron pressure. Electrons are being compressed in the white dwarf. So they want to go to the next level. So they actually get energy.
They can't go beyond that first. They can't go beyond that first orbit.
No.
Collapse too.
I don't think you quite grasped it. Let's say the second level, you can only have 8 electrons. That's it. If you put 8 electrons in the second orbit of the atom, you filled it up. That's it. Second orbit filled up. Then you have to go to the third orbit. If there's a new electron that wants to join them and party, like 9th electron, it goes to the next orbit, like that. The next level, you can have 18 electrons. If you put 19, it goes to the next one, like that. So that's what electron pressure is. Electrons wants to go to the next level. They're being compressed. They go, I want to go to the next level. I want to go to the next level. So as they try to go to the next level, they energize themselves, and that's what stops the collapse of a white dwarf. It's kind of complicated.
Okay, I understand. Thank you.
Look, Channel Sekar figured that out at 18. And I'm 67. I couldn't figure it out. 18 years old, Channel Sekar figured that out. Amazing. Sheesh, man. Some people are just amazing. Like Einstein, amazing. What kind of a brain is that? All right, make sure you guys read about solar wind. Rotation of the sun. How does the sun rotate? How long does it take it to rotate? You know, all that. There's one just on rotation of the sun, actually. Rotation of the sun and, you know, solar cycle, all that. There's a little short video, like 1.5 minutes. Make sure you watch it, you guys. Like, how long does it take the sun to rotate one time? On average, let's see, what's the solar cycle? Like when the number of sunspots go up, and then they go down, and then they go up again. What's the time between maxima to maxima? How long does that take? Like the next one is 2023. Last one was in 2012. You saw the movie 2012? It was based on that, 2012.
You said it sucked, so I didn't bother.
I'm sorry?
You said that it sucked,
Well,
so I-
yeah, the Earth was getting destroyed, and they got on top of a Cessna and they left. What kind of a movie is that? How do you save yourself with a Cessna? With a twin, single engine Cessna, not even a twin engine Cessna.
unless you're Indiana Jones, it's not a thing.
Yeah, well, it happens in Hollywood.
Professor, you said there was a video on solar wind.
Yes, there's a
Okay.
video on solar wind. There's a video on rotation of the sun and solar cycle, all that. One of the videos that I made, I put it on YouTube. YouTube said that it's illegal. I don't know how I made an illegal video. There's no nudity. Well, maybe the electrons were naked. I don't know. Sheesh. Okay, we're almost done. Yeah, the spaghettification, right? Remember, Noah, you know a spaghettification, right? You told me yesterday.
Yeah, I know
Yeah.
spaghettification.
Happens into a black hole and you get turned into spaghettification.
Correct. And what is the spaghettification? That's what I'm asking you.
Oh, when
The
you're
atoms.
coming towards a black hole, it pulls one part of your body faster than it pulls the other part. So it pulls the
Why?
bottom. So if your feet are going towards the black hole, it's going to pull your feet a lot faster than it pulls your head.
So because your feet are closer, right?
Yes.
Yeah. So it doesn't even have to be like a person. It can be a star. I just read an article, a star is getting spaghettified. I think it was on, I don't know. I know where it wasn't. It wasn't on Fox News, but I think it was on maybe CNN, something like that. I don't know. They said star is getting spaghettified. Amazing. Doesn't have to be a person. Okay, so again, why can't you escape from inside of a black hole? Why doesn't a signal go out? Like if you want to help,
Because you
911,
can't go-
help me.
You can't go faster than the speed of light. And it's sucking in energy faster than the speed of light, or sucking in
Because-
mass faster than the speed of light.
Because
The gravitational pull of the singularity is much greater than externally.
Because time nor light can escape a black hole.
why?
It's-
That's the question I'm asking.
It's sucking in space faster than the speed of light.
Ah, there you go. Is that Shaw again?
It is.
Oh God, I'm getting all the points again, man. You should play Monopoly. All right. You should play Pokemon Monopoly, man.
I'm a
I-
killer at Monopoly.
Yeah? Have you ever played Pokemon Monopoly?
I've not, but I have the San
Huh?
Diego edition.
Pokemon Monopoly, you buy Pokemons and you buy like stadiums and stuff to get your Pokemons to inside of houses, Okay. Okay, let's see. I'm on question number 40. Sheesh. 44. Almost done. Okay. Okay. So what's the meaning of temperature again, you guys? Like what's the hottest part of the sun? Is
The
where
kinetic energy between
Correct.
particles.
fastest, right? Things that move fast, that's high temperature. Things that
Right.
move slow, temperature, yeah. That's awesome, man. I finally got that going. All right. Solar flares too. Solar flares. I made a video just for solar flares, you guys. Sheesh. Please watch the solar flares and the solar wind. Okay, almost finished. Question 49. The difference between luminosity and brightness. That's it.
Thank you and have a